Welcome. In the last lecture, we discussed the Cauer I and Cauer II realization, and in this lecture, we will discuss some numerical based on Cauer I and Cauer II. Here we are provided an impedance function which is s raised to power 5 plus 5s cube plus 3s divided by s raised to power 4 plus 3s square plus 1. And we have to synthesize the network using Cauer I form. To synthesize the network using Cauer I form, we have two conditions. One is the numerator and denominator polynomials must be arranged in descending order. Here we have s raised to power 5, s raised to power 3, s raised to power 1. These are in descending order, as well as in the denominator s raised to power 4, s square and s raised to power 0. So this is also arranged in descending order. The second condition is that the highest degree of numerator must be greater than the highest degree of numerator. As we can see, the highest degree of numerator over here is 5 and over here it is 4. So obviously the highest degree of numerator is greater than the denominator. So we can obtain the continued fraction expansion. To obtain the continued fraction expansion, we will divide the numerator by the denominator. So I'll consider s raised to power 4 plus 3s square plus 1 as the divisor, and in the dividend I will keep s raised to power 5 plus 5s cube plus 3s. S raised to power 5 plus 5s cube plus 3s. In the divisor we have s raised to power 4 and in the dividend we have s raised to power 5. So to obtain s raised to power 5 out of s raised to power 4, I need to multiply this with s. So I'll get s raised to power 5 plus 3s cube plus s. Changing the sign, I will get these two terms will cancel out. Out of this I'll get 2s cube and out of this I'll get 2s. Now this remainder will become my new divisor and the old divisor will become my new dividend. So keeping this as the divisor and putting the new dividend here, s raised to power 4 plus 3s square plus 1. Okay, we have s raised to power 4 here, we have 2s cube here. To get s raised to power 4, I need to multiply this with s by 2. So I'll get s raised to power 4, multiplying this with s by 2, I'll get s square plus 0. Changing the sign, minus minus minus. These two will cancel out and this will result in 2s square and this will result in plus 1. Now this is my new remainder. Now this new remainder will become my new divisor and the old divisor will become the new dividend. So writing 2s cube plus 2s here, I have 2s cube here, I have 2s square here, so I need to multiply it only with s to get 2s cube. So 2s cube plus s. Changing the sign, I will get these two will cancel out, I'll get s as the remainder. Now this is the new remainder. This new remainder will become new divisor and the old divisor will become new dividend. And continuing the division, I have 2s square here, I have s here. To get 2s square out of this, I need to multiply it with 2s. So let us multiply it. I'll get 2s square plus 0. Changing the sign, in the remainder I'll get 1. I'll keep this remainder as new divisor and the old divisor as the new dividend. Continuing it, multiplying it with s, I will get s and the new remainder will be now 0. So if the remainder here is 0, I'll say the continued fraction expansion is terminated. Now using this continued fraction expansion, I can write this z as s. I will write this z as the first quotient s plus 1 divided by the second quotient which is s by 2 plus 1 divided by the third quotient which is s plus the next quotient which is 1 by 2s and then the next quotient plus 1 by s. So this is the decomposition of the given network function in this form, continued fraction expansion form. If the given function is a impedance function, this means that this will be a impedance function, so this will be my z1s. If it is z, then this has to be a y function, so this will be my y2s. Similarly, this will be my z3s, this will be my y4s, and similarly this will be z5s. Now I have z1s, I have z1s as s. This means this has to be a inductor, because only inductor has the network function something like this. So comparing it with ls, I will get L to be equal to 1 Henry. So Z1S equal to S gives a inductor which is of 1 Henry. Similarly, Y2S will give Y2S is S by 2, and the admittance of a capacitor is S by 2. That means comparing it with CS, I will get the value of C. So the value of C will be equal to 1 by 2 farad. Similarly, Z3 of S is equal to S again. So comparing it with again LS, I will get L to be equal to 1 Henry. Now the fourth term is admittance function Y4 of S, which is equal to 2S. Comparing it with CS, I will get C to be equal to 2 farad. And the next function is Z5 of S, and Z5 of F is S. This means I will get L to be equal to 1 Henry. Now composing the network using all these elements, let me number this. Say this is L1, say this is C2, say this is L3, say this is C4, and say this is L5. As the first element is a impedance function, so I will draw it in the series. Next element is in a admittance function, I will draw this in parallel. That means the first element should be inductor. So drawing the circuit, the first element should be inductor with the value 1 Henry. The second element is a capacitor and it is admittance, so it should be connected in parallel. So connecting it in parallel, having the value 1 by 2 farad. The next element is Z3, that is it is an impedance function and it is inductor, so connecting it in series, so it will be a 1 Henry inductor. The next element is a admittance function which is a capacitor, so connecting it in parallel, I will get a capacitor of 2 farad here. And the next or the last element is an inductor which is S, that is impedance. So connecting this inductor of 1 Henry here and completing the circuit like this, and this is the required Cauer I form of given network function. So the advantage of Cauer method comes out to be that we do not need to check whether the given function, given network function is a LC function, RC function or RL function. If I perform the continued fraction expansion, then the continued fraction expansion elements will tell themselves that what kind of element they are. Like this element is saying that it is an inductor, this element is saying that it is a capacitor. So we do not need to check whether it is a LC function, RC function or RL function. Let us perform the another numerical. In this example, we are provided a impedance function which is s plus 3 into s plus 5 divided by s into s plus 4, and we have to synthesize the network using Cauer I form. Let us start by writing this network function into the polynomial form. I have this zs, and writing this in the polynomial form by multiplying these two factors, I'll get s square plus 8s plus 15 divided by s square plus 4s. Now the condition to obtain the Cauer I form is that the polynomials must be written in descending order form. So these two polynomials are written in descending order form. Also, the degree of numerator must be greater than equal to the degree of denominator. So the highest degree here is 2, highest degree here in the denominator is 2. So these two are equal. That means we can perform the continued fraction expansion. Let us start. Writing s square plus 4s as the divisor and s square plus 8s plus 15 as the dividend. I have s square in the divisor. I have s square in the dividend. So I will multiply it with 1 to get s square plus 4s, changing the sign, plus 0, changing the sign. These two will cancel out. I'll get 4s plus 15. Now this is a new remainder. This new remainder will become our new divisor and the old divisor will become our new dividend. So writing s square plus 4s here. We have s square here and we have 4s here. So I will multiply it with 4s by 4 to get s square. So s square, and multiplying 15 with s by 4, I will get 15 by 4s. Changing the sign, I will get, now these two will cancel out and the difference between these two will be s by 4. Now this is the new remainder. Now this new remainder will become our new divisor and the old divisor will become our new dividend. That is writing 4s plus 15 here. I have 4s here and I have s by 4 here. To get 4s out of this s by 4, I need to multiply it with 16. So I will get 4s plus 0, changing the sign, I will get 15 as the remainder. Now this is the new remainder, it will become new divisor and the old divisor will become new dividend. So writing s by 4 here. I have 15 here, I need s by 4, so I will multiply this s by 60. So multiplying s by 60 with 15, I will get s by 4, changing the sign, I'll get 0 as the remainder. As I have got 0 remainder here, so I will say my continued fraction expansion terminates here. Now using this continued fraction expansion, I can write the given network function zs as zs will be equal to the first coefficient, that is 1, plus 1 divided by the other quotient, which is s by 4, plus 1 divided by the third quotient, which is 16, plus 1 divided by the next quotient, which is s by 60. Now the given function is impedance, so the first element will be impedance, so this will be z1s. Similarly, if it is z1, then this will be y1 of s, so this will be z2 of s, and similarly this will be y2 of s. Now using all this information, I can draw the circuit. So as the first element is z1 of s, so writing z1 of s equal to 1. Now the impedance of any function is constant, that means it must be a resistor. So I have R1 which is equal to 1 ohm here. Similarly, I have next element as y1 of s, which is equal to s by 4. Now the admittance of any function is s by 4, that means it must be a capacitor Cs. Comparing this function with Cs, I will get C to be equal to 1 by 4 farad. The third element is Z2s, which is equal to 16. So the impedance is again coming out to be a constant, that means it will be a resistance. So R2 will be equal to 16 ohm, and the next element is y2 of s, which will be s by 60. And now the admittance is s by 60, that means it must be a capacitor Cs. So comparing it with Cs, I'll get C to be equal to 1 by 60 farad. So observing these elements, I'll get a ladder network of RC form. Let us draw the output circuit. We have first element as the impedance, which is R, so drawing resistance in series of having value 1 ohm. Then the second element is the admittance, which is a capacitor, so drawing a capacitor in parallel. having the value 1 by 4 farad. This will be 1 by 4 farad. Now the next element is the impedance. So drawing it in series, and it is resistance. So drawing a resistance in series which is 16 ohm. Similarly, the next element is a admittance function. So drawing it in parallel, and which is a capacitor. So drawing the next element as a capacitor which is 1 by 60 farad. So this is the required Cauer I form of given network function. Once again, the things to be noted about this is that we do not perform any test to check whether the given network function is a LC function, RC function, or any other function. We just perform the continued fraction expansion, and the elements tell themselves what kind of element they are. That's it for this lecture. In the next lecture, we'll discuss the Cauer II form of synthesis. Till then, thank you so much for listening.